Okay, so welcome, and I'm going to start with recap what we did last time about electric flux. Okay, and first thing first, electric flux is just something that you want to quantify the electric field lines. Okay, and because of the intuitive or the something that's now obvious to you, that the amount of lines per unit area, or you can think of it in terms of like the line density, eventually will give you the strength of the electric field. And hence, that's why we want to quantify the flux, okay? And in that business, what we had to do was just trying to define the area, to be now a vector, okay? And what we learned last time is from now on, anytime that you have a piece of area, the area vector is going to point perpendicular to that actual area. Okay, sounds cool? All right, so the notation now is going to be something like this. It's just the area vector. It's just the magnitude multiplied by the unit vector that is pointing perpendicular to it. Okay, so by having A defined in that way, the way that you calculate flux, I mean, conceptually, it's just like you want to count the amount of electric field lines that penetrating that area. However, when you want to take into account the lines, you want to count those lines that piercing through or penetrate the area in a perpendicular fashion. So that's why you had two ways of doing it. One way of doing it is just you find out what is the perpendicular components of the electric field with respect to that piece of area. Or on the other hand, because now we have already defined that area vector, you can do the components of the area vector instead and keep the electric field vector fixed. Both will give you exact same result, because what you can do at the end is now the dot product between these two vectors. Okay. And you probably remember that every time you do the dot product, it's just like you want to take the components of two vector that is pointing in the same direction, and then you just multiply them. So that means E dot A is just EA cosine theta. And in this view, you have two choices. It depends on your perspective. You can think that cosine theta is being attached to A, or you can think that the cosine theta is being attached to E. You got the same results. Okay, and that's how we calculate flux on any piece of a surface area. Cool? So far, so good?
Okay.
I hope. All right. Now, with that, that means it depends on the direction of the electric field vector and the area vector. If they are sort of like making the angle less than 90 degrees, the cosine theta is still positive, so you are having a positive flux. If, on the other hand, you have the angle between E and the A vector beyond 90 degrees, in that case, you're going to have a negative flux. Or, of course, if you have a perpendicular E and A, so that means the electric field does not penetrate the area. So in that case, you get a zero flux through the surface, okay? So flux can be positive, negative, or zero. But now with this figure, sort of like the intuition just lead you to saying that when you have a positive flux, see, it seems like that electric field line is trying to escape out of the area. Or, I mean, if we, of course, we said, what we are about to do here, we always talk about a closed surface. So the surface that we are looking at in the future will not be an open surface. It's going to be a closed, like a balloon like this. So with the balloon in it, like in this shape here, you always define your area vector pointing outward from the enclosed volume. Does that make sense? All right. So we mentioned about your hairs and on your body. That is a very good representative of your area vector of your skin surface. Yeah. So that's what it is. So with that, direction of the A is always like this, no ambiguity. So you can say that every time you have a positive flux, it seems like that flux of the electric field try to exit from your inner volume. Does that make sense? Okay. On the other hand, if you have a negative flux, it means the electric field is trying to enter, try to get in to the inside volume. Cool. All right. So that's why we concluded that every time you calculate flux, it gives you a way of saying that how much the electric field line is trying to coming out of your closed surface, how much is trying to enter your closed surface. Is that cool?
Okay.
So you get an idea of what it's trying to do right now. Yeah. Okay. So we're going to reveal the grand sort of like the underlying concepts or the techniques that we're going to use today. Okay. But at least now you understand what does it mean by positive flux, negative flux, or zero flux. So now you understand that if you have a zero flux, that means it gives no contribution. It's not in, it's not out. There's nothing to do with it. So that's kind of nice. Okay, cool. All right. So we ended last lecture with this intuitive idea or intuitive example saying that if you have something like this, see the net positive electric field, net electric flux is positive. So that means there must be something in there, right? Because the net flux is trying to leaking out. มันปลิ้นออกมา right? It's coming out of it, right? So there must be something in there generating this flux. On the other hand, the other two examples, it's saying that, hey, the electric fields came from somewhere else and it's trying to enter, but that's the amount of lines that enter is eventually exit that volume. So there's no net amount of flux in here. There's no in, there's no out because they cancel. So there shouldn't be anything in there that's generating the flux. That's the clue that we're going to do the actual calculation today. All right, but before we get to that charge or no charge or whatever inside, let's learn how to really calculate the amount of flux through surfaces. Sounds good? Having fun now?
Okay.
All right, guys, start with this. Okay, so I have a bunch of exercise that I hope that eventually by the end of these examples and exercises over here, you have a clear picture of how flux can be calculated. Consider a uniform electric field E oriented in the X direction as shown. All right, so there's like an orange electric field lines pointing in a positive X direction there. Find the net electric flux through the surface of a cube of H length L. So you have a cube sitting there as shown in the figure. All right, guys, what do you think? How are we going to proceed with this? I don't know, you guys sort of like start to see how things about to, happens here. So logically is this. Do you think which surface of this cube eventually going to get some flux penetrating through? Yeah, when you look at this one, Ajan, when I see this, I can see that, let me call this the left surface of this box. That left surface seems to get electric field penetrating through. Can you see that? Yeah. Yeah, A1, very good. Cool. And the A2 doing the same thing because this is another surface that eventually gets some electric field piercing through it. And the other four, the top, the bottom, the front, and the back, there's no penetration of the electric field lines. So that means what I can actually draw a conclusion right away. This A3, it's too thick. Okay, here's A3 over here, should have zero flux. Let me call this the top area here. Cool. No flux. The bottom here, flux at the bottom, nothing. What about the front? Let me call this the front. Nothing. What about the back? I can call this the back there. Nothing. Cool. So the only thing that you need to do the calculation is just one on the back and one on the left and one on the right, the green and the blue. Cool. All right. So let's start with the green. So let me highlight this one. So this is the one that you're going to get some electric field lines piercing through. So look at the green surface over here. The area vector of this surface is going to point backward. You guys with me, guys? Yeah. That's my A. Let me call it left vector. Cool. Because it has to point perpendicular to the actual surface and is pointing outward from the enclosed volume, which is inside the cube. But at that point, the electric field is actually pointing in this direction. With me? That's the E here. So now you can see that these two are making a 180-degree angle with each other. So what you can conclude over here now, I can do the calculation here. The flux, let me call the left, is just E dot A on the left vector. Cool. And that will be the magnitude of the E, magnitude of the A on that left-hand side, and then cosine 180 degree. Cool.
Okay.
All right. And that gives you a negative flux. Cosine 180 is negative 1. Electric field times, of course, is the L squared. There you go. Okay, it's supposed to be small L there, guys. Sorry. Okay. So that's a negative EL squared. Why is negative? Now you start to understand. The reason is negative flux because it's trying to enter the cube. That's why it's negative. All right, cool. Try again. What about the blue? Oh, okay. So on this blue, the area vector is supposed to point perpendicular outward. So let me call this the A on the right. Okay, and at that point, at that surface, electric field also point in the same direction. So let me write it in the same direction there. So the angle between these two vectors is 0 degree. So that means the flux through the right side surface over here is going to be E dot with the A on the right vector. And that is going to be the magnitude of E, magnitude of A on the right, and the cosine 0. Of course, cosine 0 is 1. So it's going to be, let me emphasize, this is positive E L squared. Cool. And what about the net flux through this cube? Well, Dan, that's no big deal now. So you call it sigma flux then, or you sometimes you're going to call flux net or whatever, up to you. It's going to be just this flux on the left, flux on the right, and flux on the side. Okay, top, bottom, left, right, I mean, top, bottom, front, back. But those already gone to 0. And you can see that flux on the left and flux on the right sides of the box is just perfectly the same, except opposite in numbers, I mean, in value. Done.
Okay.
How bad is this? Yeah, very good. 0, 0. And you can sort of like start to see why this is 0. When it's 0, it means the net amount of flux is none from this 0. So it means there's nothing trying to enter this box, this cube, and no, nothing is trying to exit from the cube. So that means the electric field sort of somehow being generated somewhere else, and whatever that gets into the box get out. So there's nothing left inside this cube. You guys with me? That's why the net flux is 0. Okay, it will get better. All right, for those of you that still confused a little bit, it will get better over time. We have a couple more exercises to go through. Okay, so try one more, shall we? Yeah.
Okay.
All right, guys. This is going with the good one, right? If you sort of understand this one, then that will sort of like a good indicator that you understand how to calculate flux and what does the, the dot product, or the I don't know. Yeah. we'll have that business going on soon. Okay, guys, take a look at this one. You have a closed triangular box resting within a horizontal electric field of magnitude. Okay, given. So once again, E is already given there. Calculate the electric flux through. Now we have a vertical rectangular surface. You have a slanted surface, and now you want the entire surface of this box. You want to give it a shot? Yeah? Okay. No need that motivation, yeah? So first thing first, they are interested in the vertical one. So it's going to be this one right here. Okay, so let me highlight that one in green. So this is the first one that they want to see how much flux is going through. And the second one that they want to see is the slanted surface. So let me highlight it in blue. So that is a slanted surface there. Okay, and at the end, they want the entire box. Okay, which I can sort of highlight this one a little bit. Just okay. All right, guys. So what is the flux through part A? Give it a shot.
Okay.
All right, I'll give you like 1 minute. So in the meantime, I will highlight that area there. So that's a green portion there that you would like to figure out the flux. Cool. All right. So first thing first, All right, for those of you that are still confused about the geometry of this problem a little bit, I think maybe it's kind of getting a little bit more obvious if you look side view. So that means if you look side view, it will go something like this. That's a vertical surface. Okay, that's a bottom surface right there. And the blue, that's a slanted surface. Cool. All right, so with that, that means if you would like to draw the vertical rectangular surface vector, look on the green first. So that means your area vector for that green is supposed to point in this direction. Make sense? Cool. All right. So let me call this a vertical vector. Cool. All right. That's a question comes in. How can something that doesn't physically exist enter something physical? Or does electric flux physically exist? I am a little confused about the idea. Very good question. And you are right. These electric field lines, these electric fields, this electric flux is non-physical. So this is a theory. This is an electromagnetic theory. So I cannot say is it physical or not, but this is the theory that allow you to explain the natural phenomena regarding electricity, magnetism, and everything. So it's just like the same question asking about, you think about the gravity and you call it a weight, which is the gravitational force pulling the weight, the mass down to the floor, right? That force, is that real? When you talk about force, you know, that's Newton's word saying that there is a force acting on it. But Einstein doesn't look at it that way. Einstein say the reason it's real to you might not be from the force, but it's because of the space-time irregularity and the mass just falling through, just sort of like travel along the curved space. That's why it's falling down to the floor. There's no force. So it's the same question that asking, like, is the force real or like a physical, you know, non-contacting force? And of course, when you have the pull, the push, it looks real because, you know, you can touch it, you can punch it, you can drag, you can all the stuff. It looks physical. But when you look at the non-contacting forces, gravity, electricity, magnetism, how real could it be? I don't know. Cannot tell. So is there a gravitational flux for gravitational field? Yes, you can do that. When I say yes, you can do that. Is there the real stuff? I don't know. But in theory, you can do that. Yeah, you can define your own gravitational flux. You can calculate the gravitational field, which is just the same as the G. But is it real? That's philosophical question. So it could be as real as you want, okay? But this is just a theory that it's trying to explaining the stuff that you can see around you. So that's why there are alternative theory that allow you to explain the same thing using totally different approach. Does that make sense? So that's why one that I mentioned to you, just for you to be able to compare, is just the Newtonian physics and the Einsteinian physics. They are pretty much, well, you can make them equivalent, but the perspective of looking at the problem are different. Okay, Newton go with force, Einstein go with curved space-time, you know, all this stuff. So, but in result, to your eyes or to your experience, they are exactly the same. So I don't know, I'm talking too much, but I hope that clear up some things a little bit. So I can clearly speak about the electric field. It's not real. I can say that. I don't think it's real because you cannot detect it. Yeah, you cannot detect electric field. This is the theoretical device that allow you to explain electric phenomena. That's the point. Yeah. Okay, cool. All right. So I hope clear things up a bit. I hope. All right, guys. So let's come back to this. It's actually a very good question, and it's very debatable. And well, yeah, it's just the way that you look at the physical world around you. Yeah, it depends on how deep you want to interpret or how deep you want to you look at your nature and try to make it as real as you want. Yeah, we might be living in a matrix or something like that. This whole thing is not real. Like we are like a code or something. All right, but that's okay. So back here, so now your area vector, the vertical area vector is pointing perpendicular to it, of course. So it's going to be pointing to your left in the bottom figure, or even want to overlay this on top. So let me draw it nicely here. So your area vector is going to point in that direction. There you go. There. Okay. And at this point, electric field is going to point to your right like this. Same thing as over here. That's your electric field is pointing like that. Cool. So with that, that means your flux is going to be negative because, yeah, you can see that then it's making 180 degrees with each other. So part A, what I can do is flux through the vertical area. Let me call it flux sub V is going to be the electric field dot with the vertical area vector. Cool. So far so good. And that would be E magnitude times the magnitude of the vertical area and then cosine 180 degree. Nice. Okay. So let me move this thing out of the way a bit. Here we go. All right. And of course, this is going to give you the negative E. Now the A vertical, that's easy, is just the height times the width. Okay. So I can just plug it in there. Oh, sorry. I need the negative sign here. So there you go. It's negative E times the height. I can put 0.1 there times the width 0.3. Done. That's it.
Okay.
All right. You can substitute E to do 10 to the fourth. No problem. But that's what it is. That's a flux through your vertical surface. Cool. All right. Now you start to see how things go. So now let's move on to the slanted surface. It's in blue. So when you look at the blue one, all right, the area vector for that slanted surface is going to point perpendicular to it. So it's going to look something like that. While the electric field is pointing horizontally. So the angle between them is going to be this angle right here. Cool. All right. But from the triangle down here, this is 60. So this is going to be 30. This is going to come back to 60 once again. So at least now you know the angle between the area vector, the slanted area vector, and the electric field. So if you go up to the above picture there in the perspective mode, your area vector will go something like this, just perpendicular to it. Okay. All right, nice. So with that, now you can calculate the flux. Let me call it sub S. So let me put this to be A sub S slanted vector right there. Cool. So flux on the slanted surface is going to be E dot with the A slanted. And that will be magnitude of E, magnitude of A slanted. And now you see that the angle between them is 60. I put cosine 60. So the only thing left for you to do is just figuring out what is the magnitude of the A sub S, which is the slanted surface right there. But that's no big deal. I know the width is still 30 centimeter. Then all I need is just that hypotenuse there. So let me call that hypotenuse X. Well, if you don't like X, I can call it S or something. Okay, S. Okay, so that hypotenuse there is S. However, you can figure out S. That's no big deal because you have a right triangle underneath. So you already know the height to be 0.1 is 10 centimeter. So from the bottom triangle over there, you can say that the relationship between the 0.1 and the S is going through the cosine function, right? It's adjacent over hypotenuse there. So it's going to be adjacent over hypotenuse is going to be cosine 60. You guys following right now? So that means I can write S is just going to be 0.1 over cosine 60. So far so good? All right, now, so my A sub S is going to be just the width times the length. So it's going to be 0.3 That's from the width there times 0.1 over cosine 60. Cool. And now I just plug everything back in here. So it's going to be E as a best is going to be 0.3 times 0.1 over cosine 60. Now times cosine 60 up here. And of course, cosine 60 can be canceled. That's not a big deal. Do you notice something here? Do you notice something here? What do you think? First of all, it's positive because electric field and the area vector are making an angle less than 90 degrees. So you're going to get a positive flux. Or if you look at the upper figure, of course, the flux is going to be positive because on the surface, the electric field lines is trying to exit your enclosed volume. So no big problem.
Okay.
So that's one is fine. But do you notice something here? So what I want you to see here is, I think the main goal of this one is this. We have gone through like the cosine 60 equal to adjacent over hypotenuse, trying to figure out the slanted area, right? A sub S. But if you look carefully at the end, the value that you got is exactly the same as the one on top. Here, 0.1 times 0.3. This is 0.1 times 0.3. And do you understand why is it now? The reason for this is because, think about this, right? Back in the day that we introduced how to calculate flux, what you did was just you breaking the A sub S into two components, the horizontal component and the vertical component, right? You guys follow so far? Okay. So what we have over here is the AS cosine 60, because you want just the components of the area vector that is pointing in the same direction as the electric field vector, right? Okay. My question is this. If you only care about this component here, just focus on this guy, the one that is deeply like put like a big black arrow over here. Just these components alone. What do you think about the actual area that is associating with this arrow right here? What is it? Of course, it has to be the area that is perpendicular to this, right? That's the definition of area vector. It goes like that. So actually, it turns out these arrow right here will eventually representing an actual area that is perpendicular to it. It has to be. It cannot be anything else. And the real, or I mean, the actual area that you really have to associate with this is going to be making 90 degrees with it. That's the agreement that we had. And do you see this? Of course, it's going to be this green area over here. This is the reason why when you do go through like this, you know, trigonometry calculation and everything, at the end, you arrive back at the same magnitude as the green area, which is the vertical one. We call this a projection operation back in the terminology of vector calculus or vector alone. We call this a projection. When I say projection, this is very easy to see, guys. Okay, think about this. You have an electric field pointing in the horizontal direction, right? If you imagine that this E right here is like a ray of light, like coming from a flashlight. Think of it that way. You have a flashlight. So what I want you to see over here is now I need a new page because I think I'm running out of space now. All right. So this one is very important, I think. I mean, if you get this one, I think everything else will be a lot easier. So what I want to do is this. So you have the vertical one. You have the bottom over here. You have the slanted one, right? Okay, so far so good. Okay, now what you have over here is your electric field vector is already point horizontally. That's not a big deal. But now I want you to imagine is this. if you think of this to be the direction of the light coming from a flashlight, for example, okay, and then you look at the blue, the blue region over here, blue, sorry, the blue over here. Oh, that's, I don't need to put on top of it anymore. Okay, so if I have a screen back here that's being placed perpendicular to the light, what should be the shape of the shadow casted from the blue area? Do you see what I'm getting at right now? What should be the shadow that you will receive from having the light going through the slanted area, the blue? Well, then of course, what you're gonna get, you're going to get, okay, let me put like a blue shadow. I want a blue shadow here. It's gonna go something like this, right? That's the shadow from the blue surface. Well, it's supposed to look black. Okay. It doesn't make sense to have like blue shadow here. All right, it's supposed to look black over here. Here we go. So that would be the shadow that you get from the blue area. But because you can see that the upper and the lower portion of this blue surface is actually matching the green. So that's why there's no doubt the projection, it's the same thing as you casting a shadow of an area onto a perpendicular screen. And you look for a shadow. See, isn't that cool? Yeah, very good. It's the same area. So you can think of this one is just like for seeing this one, oh, actually, I don't need to do anything. When I look at this one, the slanted surface, once you project it, so it's mean once you're trying to find the shadow casting on a screen that is perpendicular to the electric field, eventually you're going to get the same area as the green one, the vertical one. And there's no doubt. That's why you're going to get exact same amount of flux. The only thing that is different is just the sign. Because right now the electric flux is trying to escape from this slanted surface. So hence you get a positive flux here. Okay. And it's going to perfectly cancel with the flux from the vertical surface that you got from part A, because they're sharing the same area. Cool. And that will allow you to answer part C. Oh, this is still in the highlight mode. Part C. So for the part C now, it's going to be easy because now your total flux is going to be the flux from the side. Let me call it the side. The front, the back, and the bottom will give you no flux because there's no penetration. Flux here is 0. Flux on the back is 0. Flux on the bottom is going to be 0. Okay, I'm sorry. I put like, okay, equal to 0. Okay, right there. Just sometimes my brain and my hand doesn't really go well here. Okay. All right, nice. So what you have there is just there. So that means the front, the back, the bottom, you don't have any contribution of the flux. So you only have just the left, which is from the vertical and from the slanted. But of course, these two are exactly the same. So you get 0 once again. Done. Cool.
Okay.
All right, there's a question coming in. Is it possible for total flux to be 0? Is it possible for the, yeah, that's what we got right now. Yeah, it's 0. Oh, not, okay, not 0. Yes, as well, but not this case. And you will see very soon when you're going to get non-zero flux from a closed surface. And what you're asking, you are actually talking about the Gauss's law without knowing it. All right. But you guys okay with this? So these problems kind of like help. All right. If not, and you're still sort of like, oh, still unsure about the projection or whatever, the shadow casting from the flashlight or whatever, John, what you're talking about, try again, guys. Here, this is going to be a true testing example that showcase your understanding about the projection of the area vector. All right, you have a cone now. It's going to look more complicated here. With base, the radius r, and height h, and it's located on a horizontal table. Cool. Now you have a horizontal uniform field E penetrating the cone as shown. So from left to right. Now you want to determine the electric flux that enters the left-hand side of the cone. They don't want to ask you the total flux anymore because you guys probably can answer. It's going to be 0 again, John. That's going to be like, okay, not a problem. Have seen this too many times. So they just only ask you what is just the flux that is entering this cone. So that means they only care about the left side. So let me sort of like chop this one in half, pretty much. Okay. And they only care about what is going on the left side of this. You want to give it a shot here? All right, a quick spoiler. It's going to be super easy. So don't worry too much. All right, guys, think about it first. If you want to go like a, classic way of doing this, you probably have to think about what is going on like a piece of area over here. And you guys know that you have to come up with like an area vector. So let me call it like a dA, just make it cool, make it look like a calculus-based problems here. All right, and the electric field itself is going through your right side, right there. That's your electric field, right? So, okay, John, it's going to be negative flux for sure because the angle between them is going to be greater than 90 degrees. However, finding out the angle is going to be crazy job because the surface of the cone is making, you have to think of this in 3D. And that dA is actually pointing in some weird angle with respect to the E. And that's not an easy task for you to figure out the angle. If you really want it, it's not easy. And you have to do this at a different value, right? Because you want to look at the side surface here and the one on the back. So the dA angle will go crazy all over the place. Like you don't know how to get through this. And here comes the concepts of the projection. The E, think of it like you have a flashlight shining the light through the cone. And now you have a screen that is perpendicular to this electric field waiting on the back side of this one. Okay, my perspective is not good. Sorry. It's this. Okay, it has to be this. There you go. All right, that's better. There was different angle there. Okay, so what should be the shape of the shadow that you got from the cone? What do you think? If you put a flashlight, turn it on, shine the light on it, okay, you have a cone in between your flashlight and your screen, what should be the shape of the shadow of this cone? The answer is this dude right here. Yeah, that triangle will show up here. And that is it, guys. This is just the A cosine theta for the whole left side of the surface. You guys with me? Okay. So let's make it very easy because now you know electric field is pointing horizontally. And now you only take the components that is parallel to this E, which is just that triangle. However, because you care about the left side of the cone, so your area vector is supposed to point to your left side. Does that make sense? You're going to have to reserve the right side of the cone that's sharing the same triangle over here, but the area vector on the right side is going to point to the right. So over here, this is going to be A. Let me call it sub L. That's the left side surface over there. So that means this A sub L going to make 180 degree angle with the electric field E. So now you can get the flux through the left side is going to be E dot A sub L vector. And it's going to be the E magnitude, A sub L magnitude. And then you do the cosine theta, right? But then you know what, Ajahn, I don't want to do this anymore. It's simply just E times A perpendicular. So we come back to the original equation that we started out from. Yeah. And that A perpendicular is just the area of this triangle. So the triangle area is equal to the half times the base. The base is 2r times the height. The height is h. So it's just 2r times h. And that's it, guys. RH. And you are done.
Okay.
Don't forget the negative, all right? Cosine 180. There you go. -1. There. You are done.
Okay.
With me, guys? So far, so good? All right. So this is what I'm talking about. If you understand what it means by the projection, that will allow you to sort of make things a lot easier. All right. You don't have to go all crazy about this whole thing. Just want to give you one more examples that hopefully it will clear things up, or I hope not confuse you more. Okay. So think about this. If I have an electric field going through my face, of course, the shape of my face is kind of weird, right? There's a curve here. Crazy. But let's say if I have electric field going straight to my face, how much flux is entering my face right now, my head right now? So the only thing that you need is just take that electric field, multiply by what? Instead of going through all crazy about the angle between my area surface of my face, you just think about the light going through my face and you have a screen behind me. All you need to do is just look at the shadow of my head on the screen behind and calculate the area of that shadow, multiply by the electric field, and you are done. Make sense?
Okay.
And so that's what it means. That means when you have electric field going perpendicular to my face like this, I don't have to care about the shape of my face or whatever. I only care about the surface that is perpendicular to the electric field. And that is just going to be just the arrow, just the shadow on the screen that is perpendicular to the electric field. That's all I care about. And that's why we call it projection, because you project a light onto my face and then you get my projection as a shadow on the screen behind. Cool.
Okay.
All right, got that? Okay, so I hope you learned about how to calculate flux through, now we call it like any shape of the surface. And then I have a couple more exercises that you can look through this one in the homework, all right, that I just posted. Did I post it last night? Yeah, I think so. All right, so you guys can check it out and see. All right, sometimes the problem might look bad, but once you understand that it's just a projection and things, it's not that bad anymore. Okay, and once again, if you want to add on top of this, what is going to be the net flux through this cone, guys? You're kind of like, okay, John, the entering electric field lines is going to be the same as going out. So all you can think on in another terms, think of it like whatever that comes in is eventually going to get out. There's nothing left over inside this cone, or there's nothing generated inside this cone. In is equal to out. The bottom surface doesn't have any flux penetrating through. So once again, you get a net zero flux through this cone again, and you are done.
Okay.
Cool. All right, guys. So I think this is a good place to take a break. So you sort of like, all right. And after the break, I will eventually get you connected with the Gauss's law and answer your question. But John, I have seen all this to be like purely like net flux to be zero all the time. Is there a case that you have non-zero flux or not? All right. So that's what we're going to do after the break. Sounds like fun? Yeah.
Okay.
All right, guys. See you in 10. Okay. Take a break first. We already knew that who is responsible for these electric field lines, guys. So who doing this whole sort of like business that generating the field? Of course, it's the charge, right? So that means, the music is still on. So the charge S generating those fields. So when we have to calculate those field lines, so that means there must be some connections to the charge generating these fields. And hence this Gauss's law, guys. That's it.
Okay.
All right, so welcome Gauss's law. Here we go. The concept is very simple, all right? So what you're going to do is now you just have to use your imagination a little bit. So Gauss states that the net flux through any imaginary closed surface, which we're going to name eventually Gaussian surface to honor him. So what we're saying that any imaginary surface that is closed, okay, once you calculate the total amount of flux through those surfaces, it will be equal to the net charge inside that surface. And because we didn't introduce any constants before, so we are going to introduce constants now to make everything work under SI system and everything. So it's going to be that charge inside divided by epsilon naught. And that's it, guys.
Okay.
See, I told you simple. But of course, by saying simple doesn't mean like, okay, it's just like that simple. It means a lot of understanding of these concepts right here. So let's start with this. So let's answer me this question. You have a charge Q right there at the center. Now I have three surfaces, which they are all closed surface. So that's according to our rule. We only care about the closed surface. S1, S2, and S3. Which one has the highest amount of flux through it?
Okay.
What do you think? Okay, maybe you don't need that much of motivation here. Do you think S1, S2, or S3? Which one gets the highest amount of flux through it? Oh, we have less and less students now. All right. Is that too early here, this class? No, 10 is not that bad. Okay, guys, which one, S1, S2, or S3 has the highest amount of flux? What do you think? Very good. Whatever you're thinking is correct. The answer is they are all the same.
Okay.
Got that? Why? Look at this. If I can count, even though we cannot easily, usually we calculate, not counting, but according to this figure alone, I can count this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 lines. And these 12 lines piercing through all S1, S2, S3 equally. That's it. So the total amount of flux, they're all the same. With me? Cool. And are these flux positive or negative, guys? See, you can see that now, wherever you're thinking here, the surface area is pointing in this direction. Let's call it dA vector. And then the electric field vector is going to point in this direction. Anyway, the angle is less than 90 degrees. You know, you're going to have a positive flux. Why? Because these few lines is trying to coming out of the enclosed volume. See? So now your net flux is non-zero anymore. So that's answer your question there. Is it possible that we have non-zero flux? Yes. And now can you see when? When you have a net charge in here, guys, that's it. That is the Gauss's law. So that means flux is the evidence showing that there is some sort of like an evidence that lead you to believe it. You don't have to believe it. Lead you to exactly how much charge supposed to be inside that closed surface. So if you have a net positive flux, you must have net positive charge in there too, because the positive charge is the one who is responsible generating those fluxes. Cool. Okay.
Okay.
I make it grand, but that's it. That's the whole thing. So that is your Gauss's law, guys. You are done. So the total amount of flux through any closed surface, that's the circle sign right there, will be exactly equal to the charge included. So that's why that INC subscript is right there. It's included inside that closed surface. And then just to make unit coincide, divided by epsilon naught, and that's it. You are done. Now you're just gonna name it for short, saying those imaginary surface that you imagine, just call them Gaussian surface right there. Okay, so that means you have freedom to choose any surface you like. It doesn't change the Gauss's law. That's why S1, S2, S3, no matter you can do S4, S5, or how weird your whatever shape of your surface is going to be, as long as it's wrapping the charge Q inside, you're going to get the same amount of flux. Try again on the right, guys. What do you think will happen? What is the net flux on this Gaussian surface that look weird? Yeah, you say, Dan, the net flux is 0. Because there's nothing in there. There's no charge in there. So when there's no charge in there, electric field must come from somewhere else. So when there is electric field from somewhere else, that is going to be the enter of the flux. But then those flux that enter is eventually going to leave. They're exiting on the other side. So at the end, once you sum them up, you get exactly the same case as this one. See? The flux coming in from whoever, wherever, I don't know, is generated somewhere else. It's getting through the cone and eventually it's leak out on the right side. And that's it. The net flux is zero. Look at this one right here. See, electric field is being generated somewhere else because it's uniform. So when it's penetrating into the enclosed volume, eventually they're going to come out the same. So if that is the case, you can tell there's no charge in this box. Same thing over here as a cube. Electric field probably came from somewhere else. So that is the flux coming in equal to the flux going out. So that is the indicator saying that there must be no charge inside this cube. Cool?
Okay.
Right. So that's it. That answers your question. When are you going to get some non-negative flux? That's when you have charge inside your surface that you are considering. That's the only way, according to Gauss's law. Simple? All right, so that's why in conclusion, the Gauss's law main thing is you just have to calculate flux, just like what we have been doing. And then once you're done with that, you equate that to the charge enclosed inside your closed surface and divided by epsilon naught, you are done. The application of this one is it allows you to calculate electric field very easily without recall or without using Coulomb's law whatsoever. I'm going to show you right now. Okay.
Okay.
But before we doing that, let's answer this question quickly. Figure shows in cross section two Gaussian spheres. So that means you pick a sphere as a shape of your closed surface, and we name them Gaussian surface. So we call it Gaussian sphere. And two Gaussian cubes. So you have another shape as a cube. You call them Gaussian cubes. That's fine. That are centered on a positively charged particle, as shown in the figure. Rank the net flux through the four Gaussian surfaces. Which one is the greatest, guys? Very good. They're all the same. Not only that, I can tell that all the flux all the flux through this must be exactly Q, which is positive, over epsilon naught. I'm done. Cool? All right, so that's it. That's how easy it is. So don't think too complicated about the Gauss's law. It's as simple as doing the flux calculation equates to the charge enclosed. Okay? All right, so I have a slide explaining how to apply Gauss's law, but I think it's kind of boring to go through this without seeing what is supposed to happen first. All right, so you won't be able to understand what's going on. Anyway, the only thing that I want to emphasize right now is it's just going to be able to apply this Gauss's law easily when you have a system with high degree of symmetry. When you say high degree of symmetry means you must have some symmetry, like look like a circle, a sphere, or maybe like a mirror image, like a reflection, or, you know, there must be something that gives you symmetry. Then the Gauss's law will be very beneficial. Otherwise, then you're going to get another kind of complications because you have to do the flux calculation. You guys with me?
Okay.
All right. The flux is the problem. You have to do the E.dA. So if you pick the A, the area that looks complicated, your flux calculation will be complicated along with it. So that's why you have to choose your Gaussian surface in a clever way to make your life easier. Let me show you one here. Guys, if I have a point charge, Q, okay, what kind of Gaussian surface should I wrap around this point charge? So imagine that if you have a charge floating in space, pitch black, like there's nothing in space. You are the only charge there. So when you are the only charge in a super, you know, there's nothing there, super dark. There's nowhere else that you can tell which one is up, which direction is down. There's no left, there's no right, there's nothing. they all look alike to you in all directions. That's when you have a spherical symmetry. Does that make sense?
Okay.
Yeah, you look around, they all look the same to you. That's why we say there is a spherical symmetry. And hence, we are going to wrap this charge with a sphere. See? All right. So once you have a sphere wrapping around, the good thing about this one is when you look at any surface on this area, your dA will be in the radial direction everywhere. Everywhere, dA. Everywhere. Everywhere. See? The dA is going to point perpendicular to the sphere, and that will be a radial direction. Now, second thing is, what about the direction of the electric field? So don't forget, we don't have to use Coulomb's law. Okay, we don't have that. We're only going to use just the symmetry arguments only. Think again. If you have a charge that's generating the field, but because right now you are the only one charge in this whole universe here, you don't know what's up, what's down, what's left, what's right. So electric field shouldn't have any bias against any direction in particular. Does that make sense? You shouldn't have electric field pointing up stronger than the one that's pointing down. You cannot bias like that because they all look exactly the same. So that's why the electric field supposed to point out in the radial direction in the same magnitude in all direction as well. Does that make sense? It's supposed to be in the radial direction. So in conclusion, the area vector and the electric field vector are now in parallel. The angle between them is already 0. So what is the flux through this Gaussian sphere, guys? Let's do it. Flux is integral closed surface E dot dA, right? So far so good. But now your E dot dA is the magnitude of E times the magnitude of the A vector, which is just dA. And then now the angle between the two, now you said it's 0. And because you can use this everywhere, they all look exactly the same. They all E dA, E dA cosine 0 everywhere. So all you need to do is just you integrate across this Gaussian sphere. And that's when you get E can be pulled out because we already said electric field strength should be exactly the same in all directions. Cosine 0 is 1, so you only have integral of the dA left for you to do. So now you are here already. And what is this? It's just going to be the area of that sphere. And that is 4 pi r squared, where the small r is just the radius of your Gaussian sphere. That's it, guys. E 4 pi r squared. That is the total amount of flux through your sphere. And it's positive. That makes sense because from the figure or from the diagram, we say the electric field is coming out of your sphere. Cool? Okay. Now that's it on the left side of the Gauss's law. The right side, it say all you need is just equate to the charge enclosed inside your Gaussian surface divided by epsilon naught. How much, guys, here you have? Well done. That's it. That's a positive Q right there. You want it there. So I just put it here, Q divided by epsilon naught. That is the equation from the Gauss's law. And once you have this, now I just only want the E. I can move 4 pi r squared to the right side. Take the epsilon naught to be next to the 4 pi. Keep the Q along with the r squared. What do you see, guys? Yeah, it's Coulomb's law back here.
Okay.
That's a wow moment here, guys. Isn't that cool? So that means just doing the Gauss's law, right? You can get back to the Coulomb's law. That is so cool. All right. And this is like a jaw-dropping moment for you. It's like, wow. It's like, are you serious? Yeah. You probably don't care much about this. But anyway, that's what it is. Right? It's the Coulomb's law with the exclamation mark like that. Well, bam, that's the Coulomb's law, but derived from Gauss's law. Cool. Any questions so far? And as you can see, I hope by going back, and if you had a chance to read this one, I hope you understand more. Like, why do we need symmetry in this problem? You know, and the reason is because we want to be able to calculate flux easily. And once we have that, yeah, just slap in the Q that is inside your Gaussian surface divided by epsilon naught, and you are done.
Okay.
So this is the main reason why I said if you know how to calculate flux, Gauss's law is just, it seems to me is intuitive, because charges are those ones responsible for generating those electric fields. So it's a direct connections between the flux and the charge. Cool. Try again. Try this one. All right, it's gonna be fun. So now instead of having a point charge, now you have a ball. Having a ball with a charge distributed uniformly across this uniform, like a spherical ball of charge. Okay, so you have an isolating solid sphere, radius capital R, has a uniform charge density. Now here we go, guys. Density is here with us again. And now it's a rho, because now we have a three-dimensional charge distribution. So now this density is really talking about the charge per volume now. Good. All right, we saw the rod, which is the charge per unit length. We used lambda before, but now because we have a three-dimensional like balls of charge, so over here we have a charge per unit volume. So that means you can easily calculate the total amount of charge in the hole in this ball here is going to be just the rho multiplied by the volume. You get back the charge. So you just take the rho multiplied by the 4/3 part R cubed. The capital R is just a radius of this ball right here. That's it. So it depends on what you want to express this one. You want to express in terms of the rho, or you want to express in terms of the total amount of charge. Now it's your choice. Now the question is, find out what is the electric field outside this sphere. Outside this sphere. And because you can see that the sphere still have the spherical symmetry, because once again, if I place this sphere in like a pitch black universe, there's no up, there's no down, there's no left, there's no right, there's no front, there's no back, there's no north, there's no south, there's nothing. So they all look alike in all directions, and hence the shape of a sphere. So that's the guide sort of lead me to pick the sphere to be my Gaussian surface. So I'm wrapping around this ball with a sphere. That is my Gaussian sphere. Once I have a sphere, the easy thing about this one is your surface area vector is going to point in the radial direction. Is that cool? All right, I'm just going to have to put this on the side here. There you go. There. And because once again, because due to the symmetry argument, electric field supposed to point out in the radial direction without any bias in particular direction. So electric field supposed to point out radially as well, everywhere, equally. Cool? See? So I emphasizing on just using the symmetry arguments. I'm not using any Gauss's law or anything. It's just assuming that electric field is supposed to be pointing out in all directions. And once you have that, then once again, you have the case where the E and the dA are pointing in the same direction. Let's start doing the flux calculation. Flux is integral of E dot dA, closed surface. That's your Gaussian sphere is closed. So what you can do is just this equal to E dA, now cosine 0. And because the E is supposed to have the same magnitude across this surface, I can pull it out from the integral. You only have integral of the dA left to integrate. And what is the integral of dA? It's just the spherical surface, 4 pi r squared. I put it back in here. Done. That's the total amount of flux through this Gaussian sphere. Cool? No change. All right, so that's the left side of the Gauss's law. What do I do next? I equate this to the charge inside this Gaussian sphere divided by epsilon naught. How much charge should I put here, guys? The whole thing. You want the whole thing, because these are a whole total charge that is inside this one. And that's why you put the whole Q in here. And that's it, guys. I just move things around again. I only want the E. I can move 4 pi r squared to the right, rearrange a little bit. Bam, I get back
Okay.
the Coulomb law. So conclusion from this one is as long as you are far away, I mean, you are not inside the ball, you are outside the ball, the electric field still looks like Coulomb's law, KQ over R squared. All right. And now you have another way to express this one. If you don't want to talk about the Q, you want to talk about the rho, the charge density, that's fine. You just substitute Q with that rho for third part R cube in here. That is fine. And then you can, you know, cancel the pi, cancel the 4, or on. And what you can draw at the end is going to be like a 3 rho capital R cube over epsilon naught R, on and on. That's up to you. It doesn't matter. Okay. All right. Very cool. It's R squared down here. Sorry. Okay. Here we go. All right. So that's done. Now, the more challenging question is, what about the electric field inside this ball of charge? Interested?
Okay.
Maybe not. Here you go, guys. What about the point inside? However, you still have the spherical symmetry. So, I mean, Adan, they're all sphere, right? Because it's a ball. So you still choose your Gaussian surface to be a sphere. So, I mean, there's nothing else for you to pick now. So you still pick your Gaussian surface to be a sphere. So that's your Gaussian sphere right there. And because it's a sphere, now you start to, you know, this is your fourth time seeing this. Your surface area is going to point in the radial direction. Your electric field is supposed to point in the radial direction as well. And they're supposed to have the same all over the place because there's no bias. There shouldn't have any direction that the electric field is stronger than the other. So now you have the same scenario that the total amount of flux through the surface, and now you have a closed surface. You put a circle sign on top. It's a E dot dA, and E dot dA is going to be E dA cosine 0. E is supposed to be exactly the same all over the place. Now you have only integral of the dA left, and then you get back to this. See, fourth time seeing this. Cool. And then you have to equate this with the charge inside this Gaussian sphere, and then all you need to do is just divide it by epsilon naught, right? How much charge do you want to put here, guys? And the answer is very good. Whatever you're thinking is correct. You only care about this amount of charge. See? With me? You don't want them all because the amount of charge that is outside this ball, outside this Gaussian sphere will not be taken into account. Gauss's law said the total amount of flux only depends on the charge inside that closed surface. Whatever outside, don't care. So how much charge is here, guys? Well, John, this is easy because we know the rho. See, that's the utilities of the rho is make it so easy to use. The total amount of charge here is going to be rho times the volume. See? And you know the volume already is going to be just that small ball over there. I mean, the small scoop of that charge over there. So it's going to be 4/3 pi, now small r cube. You guys with me? Okay. So that's it. You just plug in that amount of charge here. So let me highlight that one so it make it clearer. So here, this is the amount of charge that you want to put in here. All right. And that is going to be rho 4 pi r cube over 3. Here we go. Those are all the blue there. Nice. All right. And then I just move 4 pi r squared to the right side. 4 pi r squared is right here. Epsilon naught is always there. And that's it, guys. What you get over here is just your electric field inside that spherical charge. Cool. All right. You can sort of like clean these things up a little bit, make it nice. It's going to be R rho over 3 epsilon naught if you want. Okay, so what do you see here? Now, electric field inside the ball is linearly depends on the radius, which makes sense because if you're standing right at the center of the ball, you should have 0 electric field, right? Because, I mean, it's symmetric everywhere, so electric field will eventually cancel themselves out, so you won't get any net electric field at the center. But then when you walk away from it, it's going to go bigger linearly. So if you would like to sort of like plot a graph between the electric field magnitude and the radius, where your radius of the ball is capital R right here, you can conclude that your electric field is going to grow from 0 linearly until you hit the surface of this spherical charge ball. And once you go beyond that one, it's going to fall down 1 over R. So that's depend on R. Now that's depend on 1 over R square. And you are
Okay.
cool. This actually links back to the question that your friend just asked about. Hey, do we have gravitational flux? Even though we didn't have that, but now you can think in the same way because you already sort of like rebuild this kind of like relationship between saying that electric field behaves just like gravitational field. So it's actually exactly the same behavior. Think about this ball to be our Earth. You guys know that if you go above the sea level, your gravity is actually falling down. And now you know it's going to be 1 over R square falling down when you go further and further and further, you know. But then if you dig deeper into the Earth's surface, this gives you the idea that the G, the value of G, is going to decrease linearly until you reach the center of the Earth, where you get zero gravitational acceleration. Cool?
Okay.
All right, but of course you won't be able to do that because the center of the Earth is like lava or something, like a molten rock or so. You won't be able to sit there. So Earth is not like a big piece of rock or anything, all right? But I mean, let's say if it's like a big piece of mass, and if you dig deeper underneath, your value of the G will reduce linearly from the surface of the Earth downward. Cool? All right, guys. I think you learned something here. I hope. And it's not too hard because we're going to focus ourselves with just a spherical symmetry just for today. All right. Next time, we're going to have a couple more symmetry for you to look at, but not too complicated. Don't worry. Okay, guys, the last exercise of the day, shall we? All right. We have come so far and I mean, almost there. Next week is going to be our last week of class. Can you believe that? All right. So we almost towards the end of this trimester already. Amazing. Yeah. And I still have to, grade your exam. Don't have time to do that yet. All right. But I'll try to catch up. I mean, just like same thing as last trimester again. I don't know how things can be done better. Okay. Okay. You have now. Okay. This is your turn, guys. Try it. You have a thin spherical shell. Now it's a shell. It's not like a solid spherical piece of charge anymore. So you have a shell. And what you have here is you have a total charge on this shell given to be Q, which is fine. Okay. Total amount of charge Q there. Okay. And the radius of this shell is given to be A. Okay. The charge uniformly distribute over its surface. Find the electric field at point outside and inside this shell, just like the previous question, right? But now it's the shell instead of a spherical solid charge. What is it? Solid spherical ball of charge. All right. Okay. Or it's not a point charge anymore. It's a shell. So let's start from the outside first, shall we? So what kind of Gaussian surface should you pick for the outside? What do you think? Yeah, well done. No matter what you're trying to trick me, they all look spherical. So there's nothing else for you to do. You're going to be able to pick a sphere, wrapping this around. What else can you do? There's nothing else you can do. Okay, so your Gaussian surface is a sphere wrapping around. Okay. Next, all right, so you can assign the radius of this one to be wherever you want to figure out the electric field. So let's place it at the distance R. So part A, so R is going to be larger than A. So what you have is, once again, when you draw this sphere, your surface area will point radially outward. And of course, your electric field by symmetry is going to point in all directions equally, just like before. No change. Cool. So with that, then what it means is what you need to do is just doing the flux calculation equal to the integral. This is just from Gauss's law, closed surface E dot dA. I haven't done anything yet. But then by symmetry, what we have over here is going to look like a E dA cosine 0. This is your fifth time doing this.
Okay.
All right. And now your E is supposed to be exactly the same at every point on this Gaussian sphere. Cosine 0 is 1. So you have integral of the dA left. And the integral of the dA is just 4 pi r squared. That's it. That's your left-hand side of this Gauss's law. You equate this to the charge enclosed, and then you're going to divide it by epsilon naught. So what should you plug in here, guys? You want the charge that is enclosed inside this closed surface, your Gaussian sphere. How much? Very good. All right. I don't want to trick you anymore. It's Q. That's the whole charge. That's how easy it is to apply Gauss's law. You just want the charge included inside your enclosed volume there. Just plug Q in there, and that's it. I can put the subscript here just to say this is the outside. It's going to be, I move 4 pi r squared to the right side, wrap things around a little bit, and you are done.
Okay.
So what you see over here is about done. Wait a second. The fifth time I'm seeing this is like you still have Coulomb's law. The answer is yes.
Okay.
It is. So that means this is a good conclusion that you, at least this is one of the things that you can take home with. Well, you're already at home. So this, no matter what you have, if it's a dot, a point charge Q, or you have a ball, like a spherical solid ball of charge Q, or you have a shell, a thin shell of charge Q, as long as you stay away from it at the distance r, your electric field will be just exactly the same as the Coulomb's expression, KQ over R squared. Cool. Okay, that's nice. Okay, so that's why it's very nice in the sense that I think the nature only cares about the symmetry. Isn't that nice? Yeah. So as long as the symmetry are exactly the same, the shape of the expression for the electric field are also the same. That's the beauty of our nature here. Cool. All right. What about the inside, guys? So of course, for the inside, you're still working under spherical symmetry. So you should pick a sphere to be your Gaussian surface anyway. There's nothing changed there. Okay, except now your R is going to be picked to be smaller than the radius of the shell itself. However, on the surface, everything looks exactly the same. Once you cut the dA is still pointing out in the radial direction, perpendicular to the sphere. Electric field by symmetry, I haven't done anything. They're supposed to point in the radial direction in all direction equally as well. So, still working under the same exact setup. Yeah, no change. So this is going to be your fifth time doing this. How many times has to be done this? I don't know. I lost count, but anyway, that's what it is. So the flux through this inner circle over here, the inner sphere over here is going to be integral of the closed surface E dot dA. I haven't done anything new here. And then E and dA are parallel, so it's going to be E dA cosine 0. And then E is supposed to be exactly the same in all direction. I can pull E out from the integral. Cosine 0 is 1, so it's the integral of the dA. And this one is just the E 4 pi r squared. So it's like, yeah, Dan, I'm kind of getting sick of this. So that's why this is supposed to be like the last example already, yeah? Okay, so equate this to the charge enclosed divided by epsilon naught. We are almost done, guys. How much charge should I put in here? What do you think? Anything in here? Anything in here at all? Whatever you're thinking is correct. There's nothing in here. Nope, nothing. Nada. No. Because there's no charge inside your inner Gaussian sphere, the green one. There's none. So no charge here. So charge is 0. I don't know what to do with this. So in conclusion, the electric field inside is zero. That's what the conclusion is. And you are done.
Okay.
Isn't that cool? Yeah, so what it says is just if you are inside a spherical shell with a charge distributed around, it turns out that you won't get any electric field inside. So you have a positive charge. Oh, it's still highlighting, sorry. Here. So you have positive charge, on the shell here. So it turns out the electric field inside is zero. Just to make you to give you a quick connection and maybe allow you to remember this one more clearly. I just give you a quick connection, even though it's not exactly the same, but I think this is something that you can relate to. When you get into your elevator, see your signal, the phone signal seems to die, or at least you get a very bad signal there. It's partly because electric field does not allow to be in your area there, because we can assume that your metal cage, sometimes you might get a little bit of charge there. So it's sort of like you won't get any electric field in there. All right. But I say it's just only part of it, because what you're doing is your communication. So it's an electromagnetic wave. It's not, we are not doing electric field like a static one, right? But at least that will give you some connection to, okay, every time that we have something like this, then we have no charge, no electric field inside a charged cage. If you think of your elevator cabin to be your cage. So that means that whenever you are inside a charged container, there shouldn't be any electric field in there. So that means when you get lightning strike and if you're sitting in the car, and the car is, of course, is metal and it can get charged and everything, you're supposed to be safe inside your car, as long as you don't have any parts of your body touching your car's body. So that's what it is, right? So there was an experiment, of course, back in the day that, Faraday or I don't know who, Tesla or whatever, they can still, stay inside like a super like high voltage cage and all the stuff. They'll still be safe in there, all right? But in reality, of course, it's more dangerous than that, because once again, what we're doing over here is a static. It's electrostatic. But in the lightning strike and everything, it's not static. There's some movement of charge. There are other effects. There is like a dissociation of the air around, and so many stuff going on. So, but anyway, it's just a simplified, or at least just, as I said, just to give you some connections with the something that experience can at least guide you to this one. Or another example is just like when you look at the mafia movie, and when they do like some meeting and they don't want you to use cell phone, they just throw your cell phone into the microwave, right? Because the microwave it's like an elevator, all right? So I mean, it might not be the same story here, because microwave might not get charged, but at least if that metal cage of the microwave get a little bit of charge there, electric field cannot survive inside the microwave anyway, all right? Plus, electromagnetic wave cannot penetrate well through the metal piece. So that's why the signal is going to be dropped dramatically inside your microwave, something like that, all right? Just a quick connections, okay? Whew. I hope you learned something today, yeah? All right, guys, so I think that is it for today, all right?
Okay.
And I'll see you guys on Saturday, all right? I will have some more stuff for you to deal with, and it's like a good application of the Gauss's law and lead you to another device in electronics and electricity. Cool? All right, guys, take care of yourself and stay safe, and I'll see you guys on Saturday. Bye-bye.